So now let's talk about how to use an always block to describe combinational logic. So there are certain statements that have to be inside of an always statement or an always block. If else statements and case statements, and a second kind of case statement called a casez that includes don't cares. So let's take a look at those. So here is a combinational logic block, but it's using this always statement. Instead of always underscore FF, we use always underscore comb to indicate that this should be combinational logic. And so here we have our inputs and outputs. They're 4-bit buses, and our outputs are also 4-bit buses. And we put always underscore comb begin. Notice there's no assign y1 equals a and b. It's just y1 equals a and b, and so forth for all of the other outputs, y2 through y5. And you'll notice that this is almost exactly the same as our prior module that we had, but instead of using the always block, we just use assign statements. So assign y1 equals blah, blah, blah. All of those are assign statements. Assign y2 equals, assign y3 equals, and so forth. And so in this case, it would be better to actually use assign statements because it's fewer lines of code, and there's no need to use the always block. But just to show you how you could use an always block, an always underscore comb statement to indicate that you're producing combinational logic inside the always block. So here we have a 7-segment display decoder, which is a combinational circuit that is described using an always block. So always underscore comb, and then we have this case statement within our combinational, our always block. And so remember, case statements have to be inside of an always block. And so we'll notice this is a 7-segment display decoder. So remember, our segments are numbered like this: A, B, C, D, E, F, and G is the middle bar. And so for displaying the value 0, so if data is 0, then we're going to get A, B, C, D, E, and F lit up, and G will be 0, will not be lit up, the segment in the middle. Likewise, if you have a 1, well, we just want the B and C segments to be lit up. So here we have B and C being lit up, and so forth. And so this is a base 10 7-segment display decoder, so displays 0 through 9. If it gets any other number, like 10 through 15, then, or in other words, A through F, then it just doesn't light up any of the segments. So it makes them 0. And this statement, this default statement, is required because for combinational logic, we need to know deterministically what the output should be for every possible input combination. So we need to specify the output value for every possible input combination in order for it to be combinational. And using a case statement is similar to a truth table. So if we had data, here was our data input 3 to 0, and we have our segments, our 7 segments, 6 to 0 as the output. So when data is all zeros, so this row here, data is all zeros, we want our segments to be 1, 1, 1, 1, 1, 1, 0. If on the next line we have data of 0, 0, 0, 1, now we want our segments to be 0, 1, 1, 0, 0, 0, 0, and so forth. So instead of going from our truth table to equations and then specifying the equations, we can actually go directly from the truth table to our HDL using a case statement. Remember, case statements have to be inside of an always block. So don't forget this default statement. If you don't include that, the synthesizer will say, oh, I'm not sure what to do in that case, so I'll put a latch in and keep what you had before. And so it actually may simulate correctly, but then when you go to build it in hardware, nothing works, and you wonder why. So, so make sure you always include a default statement in your case statements. And And here we have another example of a case statement, but this is called a case Z. So this is the priority circuit that we've talked about in prior videos. And so we have these question marks. These question marks right there, those question marks are don't cares. So it means that we don't care what the other inputs are. So here we have our input A, and when A sub 3, that most significant bit of A, is high, it says I don't care what the other bits are, because when that's true, I'm going to give priority to that most significant requester, or A sub 3. Will cause Y sub 3 to be 1. Likewise, if A sub 3 didn't request it, but A sub 2, that A sub 2 input did request or was high, then it doesn't matter what A sub 1 and 0 are. Those are don't cares. That question mark means don't care. And then A sub 2 gets it by saying Y sub 2 is 1, and so forth. And again, this case C statement, so in a case C statement, we can include these don't cares on the inputs. And the default, make sure to include, as just like in the case statement, make sure to include the default. For example, in this case, if we didn't, the combination of A being 0, 0, 0, 0 would not be covered.